Good morning, good afternoon, good evening, everyone. Thank you very much for coming and attending our final installment of the San Diego Big Chapter. San Diego Big Chapter. Today, we are absolutely honored to have Dr. Nereo Markulic from IMEC. He will be presenting a very nice tutorial on subsampling PLLs, which is a topic of really growing interest in the industry. Anyways, just to get some first order things, we will have a Q&A session halfway through the presentation, as well as at the end of the presentation. Okay, but if you have questions, please type it into the panel, into the Q&A box in the lower right corner of your WebEx window. Okay, so without any further ado, let's move on to the main event. So just a brief introduction about Dr. Markulic. He obtained his PhD in 2018, summa cum laude, from the Free University in Brussels in Belgium, in collaboration with IMEC on digital subsampling, phase lock loops, and polar transmitters. He is currently a research scientist in IMEC, working on RF and mixed signal circuits for radar applications and next generation connectivity. Nereo has authored many publications and patents on PLLs and A to D converters, and a book on frequency synthesis, and is co-recipient of the ISSCC 2019 Lewis Winter Award for Outstanding Paper. Nereo is one of my colleagues in the VLSI Technical Program Committee. Absolutely honored to have you here, Nereo. Good morning. Well, let's start the show. Thank you.
Thank you for the introduction, Alvin. I'll run the presentation so we dig right into it.
Great.
Good day. It's a pleasure to be part of this SSCS chapter in San Diego, virtually or not. I would like to thank Alvin for inviting me to contribute and to say that it was a pleasure to record this talk for you. This talk on subsampling PLLs for frequency synthesis and phase modulation has a certain tutorial-like quality to it, but throughout the presentation we will also look in some more complicated or recent innovation that we have developed in IMEC Belgium. This talk follows a certain bottom-up approach. So what that means is that we will start by looking into subsampling PLL basics. Then, in the next step, we will increase the complexity and extend the basic subsampling loop so that it becomes capable of fractional synthesis. In the third part, we will look into the digital-to-time converter, which is the key component that enables fractional synthesis. In the fourth part of this talk, I want to discuss background calibration techniques that can really enhance a lot the basic high-performance analog core when it comes to fractional synthesis and modulation. And in the final part of this talk, we will look into subsampling PLL-based phase modulation. A little bit of motivation at first. The subsampling PLL is really a popular architecture recently. The main reason why is because this loop offers you the possibility to achieve really great figures of merit. What a figure of merit in PLLs typically shows you is how much jitter is your loop producing given the power consumption you're using. And it turns out that the subsampling environments really show a great trade-off between these two values, both in integer n operation modes, indicated here with red circles, and in fractional n operation modes, indicated here with red squares. There are other reasons why the subsampling PLL is so popular. One of them is that to build, a basic architecture for integer n synthesis, you do not need to dig into any digitization complexity, which is typically related to classical digital PLLs. It's a simple analog loop. Basically, it's built out of a switch, a capacitor, a transconductor, and a loop filter, and of course VCO. It doesn't get much more simpler than that, and it turns out that in order to stabilize this loop, you only need to be familiar with the classical analog equations for loop stability that nobody's afraid anymore. In other words, to make a subsampling PLL, you need a good analog designer. You don't need, for instance, an analog and a digital designer that end up having to make some complex mixed mode simulations that you need to do when you're designing, for instance, a digital PLL. An analog PLL, a subsampling analog PLL, is also very popular in my opinion because it's scaling friendly, although it's an analog loop. Basically, as I said, it's built out of a switch, which is continuously improving with newer technologies. Capacitors, they get denser and higher, so they consume less area. Transconductor is anyway a component that operates in the current domain, hence is not susceptible to scaling of the supply level voltages. And the loop filter, as I said, also gets only smaller in newer technologies. Moreover, I think one of the reasons why subsampling PLL is very popular, it's a low power technique, meaning it has no dividers in the feedback path that are typically very power hungry, especially if you need to divide from RF or even millimeter wave frequencies. Okay, so let's explain how the basic subsampling PLL works. The basic operation is depicted on this figure on the left. And what's immediately important to note is that the process of phase locking is related to sampling, or to be more exact, subsampling, because the output period can be smaller than the input period. Or in other words, the input frequency that is used for sampling is much smaller than the output frequency typically. Basically, if we have PLL that is in lock, we're gonna subsample exactly the zero crossing of the VCO, which means that instantaneously we will sample the zero, which will bias the transconducting stage, which will not dump any kind of, which will not push nor pull any kind of current from the loop filter. If, however, there is a certain amount of phase mismatch between the input and the output frequency, as depicted over here, for instance, when the reference phase leads the VCO output phase, we will subsample typically some positive voltage, which will then bias the transconductor, which will then push certain amount of current into the loop filter in order to change the control voltage and consequentially the operating frequency of the VCO, which will eventually correct for presence of mismatch between the input and the output frequency and phase. The subsampling PLL is indeed a simple one, and to prove that, we will go together through a design exercise of a loop like that. Now, the idea, of course, is not to bore you too much with equations, loop stability analysis, and so on. The idea here is to highlight the most important principles and also to build intuition behind the most important effects. What's in core in our system, of course, and that's something that we will start with, is our subsampler. And the subsampler operates near the zero crossing and will ensure that we subsample some positive or some negative value which are directly proportional to the amount of phase error between the input and the output phase. What you should immediately intuitively see over here is that the slope with which the VCO passes through zero has actually a rather high slew rate, especially if we operate at high frequencies. And that should already intuitively give you an idea of the fact that the phase error detection gain in a subsampling environment is going to be large, because even a small deviation from the zero crossing will result with, so to speak, an explosion of information. If we want to mathematically express the phase error detection gain in a subsampling environment, then we can use the following equation, which shows that the phase error detection gain is dependent on the product between the AVCO and GM, where AVCO is the amplitude of oscillation of our voltage control oscillator, and the GM is transconductance of the transconductor used over here. Naturally, this equation works exclusively if we can operate in small signal approximation, or in other words, where the phase errors are small enough. This condition is typically true during normal phase lock. Hence, this equation is then valid. The transconductor is a very simple circuit that resembles a charge pump. However, it does not operate with up and down pulses you typically have in a classical environment. In fact, what's going to happen is we're going to subsample some voltage, as I explained earlier, that is directly proportional to the amount of phase error between the input and the output. This voltage will be brought to the input differential pair as a fixed value, and a certain amount of current will be produced and then mirrored to the output, so that the current can be pushed or pulled from the loop filter in order to readjust the operating frequency of the VCO. The transconductance is simply defined with the input pair GM and the mirroring ratios used. The loop filter used in a subsampling environment is exactly equivalent to a loop filter you can use in any analog environment. Hence, I will not spend too much time explaining it. For instance, I chose here the architecture of a loop filter, which offers us one additional pole at high frequencies. It's also going to have a zero in the origin, and a pole in the origin and one additional zero for stabilization. Solving equations for stability in a subsampling environment is equivalent to solving equations for stability in a classical analog PLL. The only thing that we have to take care of is once when we calculate what our open loop gain is, to ensure that the unity gain appears at 4 times larger frequency than the zero, and that the pole appears at approximately 4 times larger frequency than the unity gain. In these equations, the only fundamental difference with respect to a classical loop is in fact hidden within the phase error detection gain, which I already mentioned is larger than in classical analog loops. Let's assume, for example, that we want to build a system for synthesis of 1 GHz at the output with 40 MHz at the input. We prefer to have a loop with a megahertz of bandwidth, and we're going to use a transconductor in it with 100 microsiemens, KVCO of 100 MHz per volt, and AVCO of 1 volt. For stabilization purposes, we desire to have the zero at approximately 4 times lower and pole at 4 times larger frequency than the unity gain. It turns out that to stabilize this loop with the reasonable parameters that are indicated over here, we need a rather large stabilization capacitance, almost a nanofarad. And this comes due to the fact that the phase error detection gain is really large, so we need a large capacitor to stabilize the loop. Even though the transconductance that we are using over here is not necessarily extremely large, we still end up having a large capacitor. There exists a very effective technique that can be used in order to reduce the filter size, and it involves redesigning a little bit our transconductor. So there is only going to be a small change. Instead of pumping the current to the output of the transconductor throughout the full reference cycle, we're going to do that only during a certain opening window, a pulsar opening window. And this opening window has an amount of time that is only a fraction of the overall reference period. And this will proportionally decrease the phase error detection gain. Note that the pulsar opening window can have several nanoseconds, and it's completely independent of the instantaneously measured phase error. It only is fixed so that we reduce proportionally the phase error detection gain. By choosing the pulsar opening window of 3 nanoseconds out of available 25 nanoseconds we have at 40 megahertz, we can now operate with a much smaller analog capacitor of 100 picofarads in order to stabilize a loop and not consume too much area. That the subsampling PLL operates without any divider in the feedback path. Although it operates without any divider, we still can have our output phase at n times higher frequency than the input phase, or in other words, our output frequency is at n times larger frequency than our input, but the multiplication is only virtual. There is no physical multiplication. What that also means is the following. Our subsampling PLL can in fact lock to any integer n multiplication number in theory. The zero-crossing subsampling process will actually remain intact independently on whether we, for example, pass 4 VCO cycles, 5 or even 6 VCO cycles in between two sampling events defined with the reference period. So that means that our PLL is completely oblivious to the integer n multiplication factor and could lock into false frequencies or undesired integer n multiples of our reference frequencies if we are not careful enough. To ensure that the subsampling PLL locks to an accurate frequency, we typically make use of an auxiliary loop. This auxiliary loop is typically built out of a classical PFD detector that operates with a certain dead zone, which means that the auxiliary PFD loop can produce up and down pulses which will change voltage on our loop filter and the operating frequency in the VCO, but these up and down pulses are going to be activated only when the phase error is outside of some dead zone range. Once when the correct frequency is acquired, and once when the phase errors between the input and the output fall within the dead zone, then the subsampling loop takes over, and there is no more influence from the auxiliary loop onto the performance of our PLL. What that means is that the auxiliary loop can typically be implemented without too much hassle. For example, it can also consume very little power so that it doesn't impact your overall performance, or it can be even optionally disabled. Now, I did explain the basics of the loop, but I did not show you where the superior noise versus power trade-off comes from. In order to explain why the subsampling loop is superior when it comes to phase noise performance, let's first look into what are the main contributors to the overall phase noise in a classical environment. We will note that the in-band phase noise is mainly dominated by the charge pump noise, by the divider noise, and the reference noise. This noise is also low-pass filtered in the transfer to the output, which means that if you make a wideband PLL for filtering the VCO noise, you will end up passing a lot of reference noise, a lot of charge pump noise, and a lot of divider noise through. When it comes to power consumption, typically the dominant power consumer in this kind of environment are the dividers, the charge pump, and the VCO. The subsampling loop is a loop which enhances in-band performance, so we will concentrate on the in-band noise generators. To explain why a subsampling loop operates with a higher phase noise performance given the power consumption in comparison to classical analog loop, we first need to do a comparison between the phase error detection gain in a classical environment that uses a PFD charge pump and in a subsampling environment. So in a classical environment, you might end up in a situation where there is a certain frequency that we have at the output, a certain signal that operates with a certain amount of phase error with respect to our input reference signal. Let's assume that the phase error is such that an up pulse of certain duration is produced, which will of course enable the charge pump current being pumped into the loop filter. The current we will pump into the loop filter on average depends of course on the amount of phase error. It depends of course on the biasing of the charge pump, and most importantly, it also depends on the refresh rate of the PLL, or in other words, how often we do the comparison. Obviously, if we compare more frequently, the up pulls will happen more frequently, because, for instance, you could end up in a situation where you have the same exact frequency at the output, you could have the same amount of phase error with respect to the rising edge of our input signal, and what that is going to result with is creation of the same exact up pulls. But if the original input frequency is smaller, or in other words, if the period is larger, in this case twice the original period, we will produce these pulls 2 times less often. So the average current is going to be reduced by a factor of 2, or in other words, in general, by a factor of n, where n is actually the multiplication factor of our PLL. What this intuitively tells you is that the phase error detection gain in a classical environment is very dependent on the multiplication factor. And when we are doing multiplications to high frequencies, this n is typically large, meaning our phase error detection gain is inherently very small. So you typically need to consume a lot of current in order to increase it, if you desire to do so. On the other hand, in a subsampling environment, our phase error detection gain is completely independent of the multiplication factor. So, for example, you might take a sample on one rate, or a sample on a different rate for a fixed phase error between the input and the output signal. We will always subsample the same error and produce same amount of average current to the output, completely independently whether we sample on one or the other rate. One small detail to note is that this pulsar opening window versus the reference period ratio is kept fixed independently of the multiplication number n, which is really easy to get. So in conclusion, our phase error detection gain in a subsampling environment is completely independent of the multiplication factor, which means that inherently you will get something that is much larger, especially at higher multiplication numbers, than in a classical loop. Hence, it will be necessary to consume less power in order to get high phase error detection gain. So why is the story on phase error detection gain important? Well, it's important because when you look into the transfer function of, or in other words, if you look into the way that the charge pump noise is transferred to the output of the system, it's actually suppressed by the phase error detection gain. So what that means is that you can benefit a lot from a large phase error detection gain. And in classical PLLs, as I said, this is dependent on the division factor. So if you have multiplication with high frequencies, it also means that the phase error detection gain is inherently very low, and you need to consume a lot of power in order to increase it. Hence, typically a classical loop has a really poor noise versus power trade-off. In a subsampling environment, this phase error detection gain is inherently much larger. Hence, you have to consume much less power in order to suppress the transconductor noise. Moreover, equally important, there is simply no divider. There is no division-oriented power, nor is there division-related phase noise. Hence, this inherently creates a situation where you have much less in-band phase noise. In fact, it turns out that typically you're going to be limited with the reference noise, which is the best situation that you can have, because typically at the input we have really low input phase noise crystal oscillator. Hence, the phase locked loop can operate with wide bandwidth. It can correct for a lot of VCO oriented noise, and in this way achieve very high figures of merit. Let's look into how we can enable fractional synthesis using a subsampling PLL. Classical PLLs achieve fractional division by using programmable dividers in the feedback path. These programmable dividers have in fact integer n accuracy, which means that they fundamentally serve as counters of a certain amount of integer n VCO cycles, right? So their quantization accuracy is related to one full VCO period. So for instance, if you want to divide by a fractional number, for example 100.28, 25. That means that you will have to divide for a certain amount of time by 100 and then certain amount of time by 101. Or in other words, you'll have to count 100 cycles for a certain amount of time and then for some time 101 cycle, so that on average you get the desired counting number or desired division factor. What that is going to result with is having certain amount of instantaneous errors that are injected into the system, and these instantaneous errors will appear at periodic rate. Hence they will induce spurs in the system. Often we refer to these spurs as fractional spurs. Spurs are problematic when they appear in band, and that's going to happen when the fractional division numbers are very close to an integer n number, because then the signature of the division factor or the periodicity is very low, and we will have small variation which results with large spurs in band of the PLL, and you don't get any benefit from the PLL based filtering. And the amplitude of these spurs is fundamentally related to the amplitude of the error that is injected into the system, the instantaneous error, and that one is related to the quantization accuracy of the divider, and the divider can count only a full VCO cycle. So food for thought could be, what if we had a divider which can count a fraction of a VCO cycle, for example 1/10 or even 1/100th of a full VCO cycle? Well, if you had that kind of a divider with that kind of fractional accuracy, you could reduce the fundamental spurs below the noise floor. We will see later on that something like that is possible to be implemented. There is no divider in a subsampling PLL. There is also no phase modulation capabilities in a subsampling PLL. So let's look into how we can synthesize fractional channels using this loop. Integer n synthesis, we're taking a sample every integer number of VCO cycles. For example, in this figure we have multiplication by 2, where every 2 cycles we take a sample near the zero crossing. If we want to multiply with a fractional number, such as 1.75 in this example, it will be necessary to continuously modulate the sampling event. What do we mean by that? So in this example over here, we have two VCO waveforms. The original VCO waveform is given in black for the exemplified multiplication by 2. In red is the multiplication example of 1.75. We can assume initially that both waveforms start in the same phase initially. That also means that the original sampling event can happen at the same position for both of the waveforms, and we will actually subsample exactly the zero crossing for both of the waveforms. In the second sampling event, in order to still subsample the zero crossing of the fractional channel we are synthesizing, it will be necessary to delay the sampling event for a quarter of a VCO cycle. In the following sampling event, this delay that we need to impose on the original sampling event to still subsample the zero crossing of the red waveform is a little larger. It's in fact twice larger. We need to delay the sampling event by half of the VCO cycle. In the third event, the delay that we need to impose is 3/4 of a full VCO cycle, and thanks to the phase wrapping mechanism, in the fourth cycle we can again subsample exactly at the reference edge and still subsample the zero crossing of the VCO. So in order to have a fractional lock, in order to maintain the zero crossing subsampling, we need to bring certain way to phase modulate the sampling event, and we can implement that with a simple digital to time converter. So the digital to time converter is a block that can instantaneously modulate the edge at which we will subsample. Note that this DTC needs to cover at least one full VCO period of delay in order to enable fractional synthesis. The computational path in front of the DTC is fairly simple. Basically, you need a delta sigma modulator. In this example, it's only a first order delta sigma modulator, which intakes the fractional multiplication number and produces at the output a stream of integer n values that on average give exactly the division factor which we want to achieve, but instantaneously on the integer n values. In other words, this ds number will simply jump between 2 and 1 so that on average it gives 1.75. The diff value is simply a result of subtraction of the original multiplication number and ds, and as such will jump between 0.25 and negative 0.75. After that, the diff value is accumulated or integrated in such a way that a triangular waveform is produced. This triangular waveform or sawtooth waveform is exactly direct representation of the amount of delay you need to create with the DTC in order to subsample the zero crossing for the given fractional multiplication number. So what that also means is that you don't need in principle delay larger than a full VCO cycle in order to maintain an accurate fractional lock, because this ACC value, the green signal, never goes above 1. After that, the only thing that it's left to do is, of course, to scale this value to the DTC input. And since we have still in what in theory is a number with fractional accuracy, or with floating accuracy, we need to round it to the available DTC input range. Let's assume for a moment that we can operate with an ideal DTC. In this kind of environment, we will be able to always subsample the zero crossing, and our original loop will in fact remain completely intact. That means that using a DTC opens up the possibility to really have no difference between integer n or fractional n performance. And what I mean by that is an ideal DTC can enable true fractional synthesis or fractional division that we were dreaming about a couple of slides ago. And this slides in stark contrast to classical loops, because with an ideal DTC, you actually end up in a situation where there is no spurs, no fractional spurs at the output. Unfortunately, of course, a DTC is just a data converter, which means that it will have limited resolution, random, noise. It also could have some gain, imbalance, or nonlinearities. And these have to be carefully assessed not to impact your performance too much, especially since a DTC is at the input of the system. So that means that all the non-idealities at its output are going to be multiplied by n squared in transfer to the output. So we have to be careful. All the errors are also low-pass filtered by the PLL, as we know, as all the other noise coming from the reference of the system. This is the reason why we will now dedicate a full section on how to design a digital to time converter. Simple DTC can be implemented as a tunable delay line. To the input of this delay line, we bring a square wave, which will induce discharging with variable slope depending on the amount of capacitance at the node Vx, and second inverter in the chain or comparator in the chain will restore the steep slope, and this steep slope can be then used for sampling purposes. Note that the DTC input and output have the same exact frequency, they're just shifted in phase, and this phase shift is programmable. Now, intuitively, you should already notice that it's actually fairly easy to achieve delay modulation with 100 femtosecond accuracy. And this can be achieved by sizing the changing capacitors and the driving strength of the inverter. And I can already tell you now that since this value over here is much smaller than a full VCO period, the quantization noise induced by this DTC can be kept below random noise floor that we have in the system. Indeed, the DTC quantization errors can be low, but you can also shape them. As I showed earlier, there is this DTC quantization path, but you can also place an additional delta sigma modulator in front of the DTC itself, which serves for digital shaping of the quantization residue. So for instance, you can in fact shape all the quantization noise out of PLL band, where it will get inherently filtered by the PLL. We know the PLL is a low-pass filter, and in this way we can really operate with phase noise levels due to the quantization noise of the DTC that are very, very well below the other noise sources. The equation that guards the amount of phase noise in band of the PLL is shown over here, and you can see that if you put numbers in this equation, you can see that even at 10 gigahertz or so, you can get in-band noise so low that it will virtually not impact your overall performance. So quantization noise can be kept low enough, but what about analog noise or white and flicker noise that are incorporated in our delay generation mechanism? So if you have a delay line, as I explained earlier, there is definitely one transistor, for in this case can be modeled as a saturated current source, which is going to discharge the relevant node in the system and as such create delay. This is actually the programmable slope we talked about, and of course the programmable slope can be programmed with the amount of capacitor that loads this current source. What's very important is that this discharging will be impacted both by flicker and white noise. It turns out that the white noise is proportional to the amount of delay we're creating, but also reversely proportional to the discharging strength of this saturated current source. So for the largest delay, you can always increase power consumption so that you get the noise low enough, at least the white noise contribution. To do the same with flicker noise is not so trivial. If you do an analysis, you will notice that if you have such an environment, in order to reduce the flicker noise, typically you need to increase both width and the length of the discharging transistor. Especially, you know, in these new nodes where the 1/f corners is at very, very high frequencies, this can be a problem. And the consequence of this is going to be that the previous stage inverter over here is going to be heavily loaded, which means that when it instantaneously toggles, it will pull large amount of charge from the supply and potentially create a large ripple on the supply. And these ripples can easily be incorporated in your clean linear discharging slopes. And this is something that can create distortion in the system. So basically, when it comes to these digital to time converters, you have to be very careful because any kind of digital delay line is very susceptible to noise in the supply, because it's all going to be incorporated into your signal eventually. So in order to reduce the problem, what we typically do is we use RC-based discharging. And what I mean by that is this R is really a polysilicon resistor, which is now an order of magnitude larger in resistance than this NMOS, which is now used as a switch and not as a current source. So what that means is that the overall discharging will be exponential, but we will still have delay as a linear function of the amount of loading we have at the output of our delay generating machine. Since the discharging is determined completely with a polysilicon resistor, which dominates the resistance in this branch, there is no flicker noise contribution, and the white noise can be easily kept below the desired level. Since this transistor now is only a switch, it can have minimum length and certain width, but overall it will not load the previous stage too much, which means when the previous stage toggles, it will not create too much ripple. And even if there is some ripple on the supply, it will only modulate, you know, the resistance of this switch, which is already an order of magnitude smaller than the dominant polysilicon resistor. Hence, it will not impact our discharging slopes, and it will not add into distortion in the system. Turns out that code dependency in our power consumption is rather problematic in these digitally intensive environments. And in order to suppress potential distortion that these effects can induce, what we typically do is we, in parallel to our delay stage, also use a delay stage replica, which is always loaded with exactly complementary code. In this way, we ensure that always the same amount of charge is pulled from the supply, and there is no code-dependent ripples or dips on our overall supply. Also, very importantly, the comparators that are used in our main path in order to restore the steep slopes, which are then used to drive the sampling mechanism, also toggle at a code-dependent moment in time. So in order to protect our overall supply, we typically regulate the internal supply of the comparators so that this instantaneous dip does not propagate elsewhere in the system and create distortion. Last consideration which I want to talk about when it comes to DTC design is the limited bandwidth of the comparator. Basically, these comparators which restore the steep slopes in order to drive the sampler typically are not completely independent of the input slope. What that means is that they will not instantaneously flip, and hence they will create some code-dependent variation or distortion in the amount of delay that is produced. So the larger the range you need to produce with your DTC with variable slope, the larger the nonlinearity. This nonlinearity is not, extreme. It's not necessarily very problematic, but just to give you an idea, you could have 0.2% of INL of the full range, given the range is 500 picoseconds. Solutions to this nonlinearity are typically in constant slope DTCs. They are not covered in my presentation, but you have to go through the same set of considerations which I showed earlier if you build one, or you could look into calibration, which I would in fact recommend. But that's a discussion for the following section. In general, I showed here that a DTC can operate with low quantization noise, which means that it will not limit your performance of the PLL. And also, if you're careful enough, you can get the low random analog noise. So in principle, there is really a possibility, a realistic possibility, that even with a realistic ADC, you can maintain close to integer n performance, although you're operating in fractional-N mode. As we will see, this has to be guarded with some digital calibration techniques, but nevertheless, the fundamental idea works. And a DTC can provide, a DTC-based PLL can operate with very good phase noise performance. I want to say that a DTC-based environment really is a powerful environment, independently whether you're synthesizing frequency using subsampling technique or some other technique. Why is that? So let's for a moment compare a DTC to a TDC. A time-to-digital converter is basically an analog to digital converter because it transforms an analog value, which is in this context time or a phase error, into digital information. A DTC is a duck because it transforms digital value into analog information. And they both serve in principle for phase error detection in your phase error detection path of the PLL. So if somebody approaches you and asks you, look, would you like to design a DTC or an ADC in order to perform the same exact task? I would personally choose a duck because duck is easier to design and it typically can operate with higher performance than an ADC. In fact, an ADC has a duck as a building block. A TDC in this context typically operates with quantization accuracy related to a single gate delay, which you typically encounter when you go for a straightforward vernier line implementation. And this delay is typically in order of 10 picoseconds, even in some advanced nanometer CMOS. On the other hand, a delay line, as I said earlier, can easily operate with an order of magnitude or 2 orders of magnitude lower quantization error. Hence, this should give you an indication why a DTC-based environment is, is always going to outperform a TDC-based environment. Today's digital PLLs are becoming more and more DTC based. It turns out you can elegantly use both a DTC and a TDC in your phase error detection path. Since they can be used for the same purpose, you can cover increasingly larger range with a DTC for phase error compensation and then operate with your time to digital converter on a decreased range. And as I said, as I argued earlier, a DTC is more efficient than a TDC when it comes to added quantization noise into the system. And this DTC phase favoring trade-off has recently resulted in a large popularity of single bit DDCs, where basically most of the work is covered by a digital to time converter, and then a TDC exclusively operates with the bang-bang operation and provides only a single bit information towards the output. When it comes to DTC-based environments, it is also possible to make a DTC-based digital subsampling PLL. This can, for instance, be done by putting a quantizer or an analog to digital converter after the sample has been taken. Note that the ADC will produce some additional quantization noise into the system, but this one can be typically suppressed again by the high phase error detection gain, which can also even be enhanced by some amplification. There is also added quantization noise that we have to handle of the DCO, but if the loop filter sizes are priority, you can also look into DTC-based digital subsampling PLLs.
All right. Pardon. So at this point, we are somewhere midway the presentation, and in order to break a little bit, you know, the video, I would like to answer a couple of questions, if there are any.
Sure. So, folks who are attending the webinar, if you have some questions, please type them in the Q&A pane.
Oh, I see the questions that are typed in. I see here the one question saying the following. So, subsampling receivers are famously bad for noise because of noise folding due to subsampling. Is there any analogous noise folding problem in subsampling PLLs? So, well, let's forget for a moment that subsampling PLL is called subsampling. Or let's just think in general about a PLL. So in any PLL, you detect information about the error on a much lower rate than at which the VCO oscillates. So in principle, no matter what kind of phase detection mechanism you have, you always subsample the information about the phase error that you have at the output. So in that sense, there is no difference between a subsampling PLL versus any other digital or analog PLL. You always have the same mechanism there, right? Okay, so does the second question is, it's a little bit awkward to answer questions like this without having feedback from the person who asked the questions, but if this answer is non-satisfactory, I can come back to it, and that applies also for the other answers. So the second question is, does the fractional-N PLL output frequency depend on the DTC gain? If not, please explain. All right, yeah. The DTC gain is crucial here. So let's think for a second about what the purpose of the DTC is. In integer n mode, we inherently always subsample the zero crossing. In fractional modes, DTC serves for compensation of the fractional residue. So let's say we operate a VCO at 10 gigahertz, that is 100 picosecond period. So that means that our DTC needs to sometimes compensate up to 100 picoseconds of phase error in order to still make the PLL sample the zero crossing, right? So sometimes it has to compensate, say, for example, 79 picoseconds, sometimes 17. And if there is a gain error on it, it will instantaneously inject a small error into the system. So for example, instead of subsampling exactly 17 picoseconds, it does 17.5. That's what happens in presence of a gain error on the DTC. And that will cause instantaneous modulation of the PLL output. It will create fractional spurs. So you will still on average have the same exact, the frequency you desire to have at the output, but there's going to be some fractional spurs. Just like instantaneous timing errors in classical PLLs cause fractional spurs, but on average you have the accurate frequency at the output. And the third question, do DTC need calibration when temperature or supply voltage change, for example? So short answer to this is yes. You need to make sure that DTC operates with background calibration if you want to industrialize the concept of DTC-based PLL. And in fact, this is what the second half of this presentation covers. I see no further questions.
Nereo, I do have a question to ask. Earlier on, you mentioned obviously to prevent false locking to harmonics, you need a phase frequency detector to basically snap the loop out of harmonic locking, right? Mm-hmm. How critical is the keeping that leakage low in what you squirt back after the dead zone filter to make sure that you're not introducing from that phase frequency detector basically reference spurs.
Right. So your question is about how do you ensure that these two loops can work together, kind of?
That's one thing, but more explicitly, like when you have the phase frequency detector squirting back a signal, right? Let's say I mean, ideally that phase frequency detector, when you are in lock, it should just be shut off completely, right? Or it should not send the signal back. But invariably there will be some leakage that's going to spill out of the dead zone dead zone block after the phase frequency detector into the control voltage. How does that? How critical is that to suppress that leakage?
You're really talking about analog leakage.
That's right.
A small drift. Well, in my experience, you can keep that to levels that are low enough, so that it's similarly like you have leakage also on the analog capacitor, on everything that it's connected to that loop filter node, and that needs to be just kept low enough so that the subsampling loop can maintain its lock independently of that. In principle, that's typically not an issue. So the subsampling loop, once when it locks, it does have it is capable of maintaining the frequency lock. So any sort of leakage is going to slowly create a phase error. It's going to accumulate over time, but the subsampling loop is going to correct that on average. So that just works in the phase lock without the acquisition loop. So the acquisition loop, the frequency acquisition loop, is not necessary anymore then.
Okay, thank you. If there are no further questions, I'm having a WebEx glitch on my side where I cannot see your questions, unfortunately. So thank you. I'm glad you're able to see it. If there are no further questions you see, I mean, please continue with part two.
Okay, I got a follow-up question, but that I will read immediately, if that's okay still, or should I?
Please, yeah, go ahead.
Right. So if the DTC gain is zero. DTC gain is zero, then the PLL frequency is definitely wrong. No fractional behavior. So is there some DTC gain greater than zero when the PLL output frequency suddenly is perfectly correct on average? So if the DTC gain is zero, so we're not, then the PLL frequency is definitely wrong. Right, so if the DTC is non-existing in the loop, then we just have integer n behavior, in other words. So if is there some DTC gain greater than zero when the PLL output frequency suddenly is perfectly correct on average. Ah, okay. Okay, that's an interesting one. So right. I the thing is that we maybe you could, for example, end up in a situation where your LSB of the DTC should be, let's say, 1 picosecond, but it's 2 picoseconds instead. And then you do create exactly 2 times the amount of delay that you should have. And then you can end up maybe in a situation which is described over here. However, we typically ensure that these errors are much smaller. Like it's not a factor of 2; it's maybe a factor of some small percent of that you start with, and then the background calibration loops ensure that the DTC gain really converges to exact number that you need. In principle, yeah, I should think about this some more. But in practice, this is not a situation you encounter thanks to the fact that the DTC gain is calibrated.
So Nereo, a couple other questions that I see in the chat window. Should the VCO output be sinusoidal? What happens if you have, for instance, a ring oscillator where you have square waves coming out?
Well, you don't, in principle, need a sine wave. You only need to have, there are subsampling PLLs that operate also with ring oscillators. The only thing you need to ensure is that you have some control over the slope which is being sampled, because that slope determines your phase error detection gain. So you need to take that slope, which can be sensitive in sensitive to say analog inaccuracies. You need to know what slope you have so that you can bias properly your loop, so that you can stabilize your loop properly. So yeah, any kind of, I mean, not any kind of, but you can permit other analog waveforms but a VCO. You anyway lock close to the zero crossing of the VCO. And so you're looking at this very small signal range around that zero crossing, and as long you have controllability of what that slope is, it doesn't necessarily have to be a sine wave.
So along these lines, I mean, wouldn't it be pushing this point to the limit? If you have, for instance, a ring oscillator output where the waveforms are much sharper, your phase frequency detector gain is going to be much higher. Wouldn't that play to the benefits of a subsampling PLL even more?
Yes, and if you push it to the extreme, you actually get to bang environments, but then the equations with which the loop operates change a little bit, because you have a statistical phase error detector and no longer a linear phase error detector. So the answer to this comment is yeah. I mean, in principle, yeah, you can permit even higher slopes, and you can still have a functional environment.
Thank you. And another question that came up is the dead zone in the auxiliary loop that I was asking about from the phase frequency detector adjusted based on the divider ratio?
Is it the adjusted divider? So typically the dead zone, in order to ensure that you have, non-ambiguous lock, it needs to be half a reference period, and then you can, and then you're sure you're going to lock to the frequency you need. So in order to, yeah, beyond that, I mean, there is. I would need to let's say open up waveforms that I don't have in the slideshow, but trust me on this one. So if it's that size or smaller, then you have no issue with the locking, the frequency acquisition.
Got it. I think, Nereo, in the interest of time, let's proceed
Right.
with part 2, and then I'm sure we'll address the other questions at the conclusion of your talk. Thank you.
Okay, thank you very much. So I'll continue the talk now.
Following section, we will look into randomization and background calibration techniques that can help with non-idealities of the DTC. So I want to recall that the input to the DTC is in fact a periodic signal, right? Because we have to compensate for a periodically accumulated fractional residue. The DTC cancel the fractional residue, but with certain accuracy. If we had a completely linear environment, the zero crossing subsampling is very accurate, but if there is a certain amount of gain errors or INL error in the DTC transfer function, we could end up having certain amount of error propagating through our loop. Error injected into the system has the signature of the fractional multiplication number, because the periodicity of the signal brought to the input of the DTC, or in other words, the delay that the DTC needs to produce, is very periodic. Hence, any kind of non-ideality will also create periodic errors, which result with fractional spurs at the output. And these fractional spurs are injected at the input of the system, which means that they are nicely low-pass filtered in transfer to the output. But for deep in-band frequencies, again, you do not get any filtering. Now, I don't want you to think that this is a specific problem of DTC-based environments, because it's not. Non-linearities or gain errors in the phase error detection path are a problem present in classical PLLs. They are typically related to the mismatch between the up and down pulse. They are also present in digital environments. So for example, you have the same problem if a TDC has a non-linear transfer function or has a gain imbalance. Equally, the DTC is a problem in DTC-based environments, because DTC is the core building block in the phase error detection path. I would even argue that the problem is by using a DTC already smaller than in the other environments. But let's see how can we deal with this problem. First of all, you could randomize the error that the DTC produces. And this is really trivial in subsampling environments. You know, I said earlier that we subsample the nearest zero crossing when we apply the periodic input signal to the DTC, but in principle we could randomly choose any of the available zero crossings that appear after the reference edge. So for example, you could sometimes skip a full cycle and subsample the next nearest zero crossing, or skip 2 cycles and so on. And in this way you can in fact mask the periodicity of the fractional error compensation. What this results with is the energy of the spurs simply spreads into noise. So you don't see any more spurs at the output, but the in-band phase noise will rise as the consequence. In some applications, this is good enough if you don't care for the in-band phase noise, but I have to admit this kind of defeats the purpose of a subsampling PLL, because in principle subsampling PLL is a low in-band noise PLLs. The modifications that need to be incorporated in our original DTC input code propagation path when it comes to randomization are trivial. So basically we just need to create a pseudo-random number generator which adds a random integer at the input over here. Now, there is a caveat to this story, and it's related to the fact that if we do use randomization, we also need to use a DTC that can cover a larger range. And with larger range, typically we are also exposing ourselves to potentially larger nonlinearity and larger gain error. So this is kind of a trade-off of this technique that has to be taken into account. order to really cancel the problem of DTC inaccuracy, we could use the principle of predistortion. Predistortion is a simple technique that we know from DAX. The idea is, of course, if you know what kind of nonlinearity or what kind of error DTC produces, you can simply use a lookup table approach and pre-compensate the digital code that you're sending to the DTC in order to get the desired effect anyway. So for example, if you have two LSBs of error on code 100, you can simply send code 98 to the DTC in order to get the desired analog effect. Now, measuring the DTC transfer curve is not completely trivial. We are talking about 100 femtosecond delay step accuracy, and in order to measure the DTC transfer function, you typically need a lot of averaging to get to this accuracy, even with the most modern oscilloscopes available in the lab today. Even if you manage to measure the DTC transfer function, and I have some literature that points you to solution to this problem back in my references. Even if you manage to measure the DTC transfer function, it is still susceptible to PVT errors. So delay lines are simply very sensitive to supply variation, temperature variation, and you do absolutely need some sort of background calibration in order to resolve this problem. Even if you use constant slope DTCs that are more resilient to INL errors, they still necessitate some sort of background calibration. Hence, I think it's very important to look into it. When it comes to DTC calibration, it is important to note that in presence of gain or nonlinearities in the phase error detection path, there is going to be a strong correlation between the instantaneous current generated by our phase error detector and the instantaneously used DTC input code. Or in other words, the errors produced by our phase error detector over time will not be random as they would be if there is no gain or INL errors in a phase error detection path. They will be colored, or they will have a signature of the DTC input codes on them. And as I said, they will appear with certain periodicity that will create spurs at the output, but also that will create a certain signature on the instantaneously measured errors over time at the output of our phase error detector. Once again, at a certain DTC input code, you might have some positive error, which will result with sampling some, negative voltage, or other way around. And the sign of the instantaneous current pushed to the input to the loop filter will be directly related to the code that we used. In principle, in order to populate accurately our lookup table, we could measure, or let's say try to minimize the correlation between the DTC input codes and the instantaneously measured errors at the output of our phase error detector. In fact, if this lookup table was perfect, or if we had no errors, no nonlinearities in our phase error detection path, there simply would be no correlation between the DTC input code and the instantaneously measured phase errors. So we can use this correlation in order to populate the lookup table and achieve this goal. In practice, the measured current at the output of the phase error detector is an analog value, and we will implement all this calibration in the digital domain, which means that it's necessary first to convert the analog value into digital information. It turns out that it is enough only to look at the sign of the error that we are looking at, which I already talked about a couple of slides ago. So we don't need a multi-bit error detection. It turns out it's enough only to have a single bit error detection. Let's look into how is this in practice implemented. So in the core of our calibration engine, we have a lookup table which stores information on DTC gain or INL errors. If there are no errors in the system, the lookup table is simply populated with 0 values, and the original DTC code can be simply sent to the input of the DTC without any correction. Nothing actually comes from the lookup table which changes the original input. If there are certain errors in the system, if there is some INL in the system, then the lookup table contains information about these errors. And before the original code can be propagated to the output, we will look at the particular address, the address of the code that it's currently used, in order to see what is the appropriate correction value we need to subtract from the original value in order to pre-restored accordingly the input of the DTC and get to the desired analog effect. If the lookup table isn't populated with the correct correction coefficients, then the correction will be unsuccessful and we will not subsample near the zero crossing but create some systematic error that is related to the used DTC input codes. What that also means is that the lookup table needs to be updated, and we desire to make this updating in the background as the PLL operates normally. To do that, we will use the information about the error sign coming out of the phase error detector. And this error sign in practice tells us, did the DTC sample soon, late, or correctly. So for example, if we sample the soon, we might get some positive errors or positive signs at the output on average. If we sample on average a little bit too late, we're going to get a stream of probably negative ones at the output. But if we sample correctly, given the code, this stream will be zero mean on average. In any case, we can use the instantaneously measured error sign to increment, after scaling, to increment the particular correction coefficient in the lookup table. The correction coefficient we are going to address is dependent on the DTC input code. In this way, the lookup table correction coefficients slowly adjust themselves into a value which then efficiently compensates for the presence of the error in the DTC transfer curve. In this way, we will subsample near the zero crossing, and the error sign stream will become a zero mean stream per particular code, and the lookup table correction coefficients fix their position. For example, we could operate with nonlinearity of the DTC, which is indicated in this simulation environment by the red curve. Instead of actually placing a correction coefficient in the lookup table for every possible input code of the DTC, in this example a 10-bit DTC, we only use 32 correction coefficients and then piecewise linear approximation between the codes that don't have a direct correction coefficients for compensation. In this way, the lookup table does not really need to be 10-bit large. It can only, for instance, be 5-bit, or in other words, we can only have, let's say, 32 correction values in order to compensate for the complete nonlinearity of the system. You need to add a little bit of additional processing around your lookup table in order to operate with piecewise linear approximation. But this is not something that will take a lot of power or compromise your area, because it's actually simple shift registers typically. The lookup table with piecewise linear approximation can then be much smaller and not take a large portion of your system, nor have a significant impact on your overall power consumption. In this slide, I show an example of how the correction coefficients propagate towards their final value, where they compensate for the existing nonlinearity in the system accurately. You see that this propagation, the speed of propagation, can be adjusted based on the gain on this LMS algorithm, on this bang-bang LMS algorithm. The larger the gain, the faster the convergence, but with the largest gains, you might end up with substantial noise around the accurate value, which you want to avoid, not to impact the performance of the PLL. One detail that I skipped to explain so far is the way in which we extract the error from the phase error detector. As I said earlier, for lowering the phase error detection gain, our output current is only pulsed to the loop filter over a full reference cycle, which means that the useful current is propagated to the loop filter only during a specific time opening. The rest of the time you're free to steer the current to wherever you want, and you could in principle steer it, for example, to a dummy node, which is always after every cycle reset to the low pass filter potential. And in this way you can track the variation of the voltage, is going towards some positive or to some negative value, and you can put a comparator on this node which will give you a direct indication of what the instantaneously measured error is without too much analog overhead. One important detail related to the error extraction is that you do not want to have any kind of input referred offset on the extraction node. Why is that? Well, a type 2 PLL that we are discussing over here settles in a zero offset condition in which the average current coming at the output of our transconductor is zero mean by definition. Unfortunately, if there is certain amount of offset in the error extraction path, although we have no errors in the system, there is a zero mean stream coming at the output of our transconductor, the calibration algorithm will still receive offsetted stream, meaning there is, for example, going to be too many ones and much less negative ones coming in our gain calibration process or INL calibration process, and that will eventually result with drift of coefficients, which can result with additional noise or even divergence of your coefficients. One way to resolve the offset in the error extraction process is to compensate for existence of it in the digital domain. So basically what you can do is there is a way to modify the stream of positive ones and negative ones in such a way that we still get a zero mean stream. We periodically overrule the original stream to get to the desired effect. Naturally, this will add a little bit of noise in the estimation process, but it will not impact overall the operation of the PLL. I did not go to more details into implementation of this offset compensation algorithm in this presentation, but I refer to more details in the references later on. Note also that there are certain solutions where this problem is resolved in the analog domain. I think this is also a valid approach, but typically mixed mode solutions are a little bit more sensitive. Okay, in summary, I want to say that indeed, building a DTC-based subsampling PLL can result with a fractional-N performance, which is equivalent to integer-N performance. Or in other words, we can enable an environment which can operate with integrated phase noise numbers, which is equal to the integrated phase noise numbers you have in integer-N performance. Or in other words, if you're careful enough, you do not destroy the core analog subsampling loop performance. How did we achieve that? Well, I showed that you can do that by carefully maintaining the LSB of the DTC low enough with careful analog approach. The DTC can operate with low noise, low random noise, and is resilient to supply noise if you're careful with your analog design. And if there are some gain or INL errors, we can efficiently compensate for them in the digital environment. I showed you here how digitally enhanced analog can really make wonders in exploiting modern CMOS for efficient linearization and getting the best out of the high performance analog core we use in our environment. Note also that all the algorithms which are shown here can be reused in other architectures, in other DTC-based architectures, for example in digital PLLs, bang-bang PLLs, type 1 subsampling PLL sampling, digital subsampling PLLs, and so on. Last part of my presentation, I want to explore ways in which you can enhance the DTC-based fractional-N subsampling PLL also for phase modulation. What is motivation to do so? Well, first of all, we have this powerful modulation technique in our system based on a DTC. Second of all, a PLL as a phase modulator is always part of a polar transmitter. And polar transmitters have proven to be today very power efficient. They can be digitally intensive and they can operate with very high power efficient numbers. In those PLLs, the accuracy of communication is typically limited with integrated phase noise of the PLL. Or in other words, the fundamental limit on the error vector magnitude measured at the output of our transmitter is going to be limited by the integrated phase noise of the PLL. So what that means is that with low phase noise PLLs, we can achieve very low EVMs. And that can enable very complex constellation schemes. Here is an example of 1024 QAM, which means that thanks to DTC-based subsampling PLL, we could in principle achieve really high spectral efficiency. And in today's world where spectrum is a scarce resource, this is typically what you want to achieve. Now, one important challenge, as you will see, is wideband modulation, because all of this is for nothing if we cannot have wide band modulation or high data rates. In classical PLLs, phase modulation can be easily achieved through the programmable divider. So instead of only for fractional synthesis, we can also use the divider for periodic modulation. In order to achieve that, you only need to feed also the modulation data into the programmable divider. Very important in this process, we will low-pass filter the data and transfer to the output. We know that the PLL is a really good low-pass filter for anything that is injected at the input of the system. Hence, this approach has very limited bandwidth. To extend the bandwidth, people have tried to apply different pre-distortion techniques. So what that means is that you overemphasize the digital data at high frequencies so that you prolong the modulation bandwidth or extend the modulation bandwidth of the PLL, or in theory even achieve an all pass. Unfortunately, the all pass here is not easily achievable, especially because digital filters get a little bit inaccurate on frequencies close to Nyquist. But even more than that, the problem is typically that it's difficult to estimate which PLL bandwidth we have in the analog domain and which exactly the pre-distortion cutoff frequency needs to be. So this all operates with very limited accuracy. To achieve a true all-pass of the data to the output, the modulation signal can be injected twice into the loop. Once through the point 1 injection, which we know from before, and it follows a certain low-pass filtering profile to the output. For the second time, the same data is injected in the frequency domain in front of the VCO. And this data follows a high-pass transfer function towards the output. So basically what happens is that when you add these two transfer functions together, you end up having a true all-pass of the data to the output. I sometimes get a question where if you really have an all-pass transfer function to the output, what is the limitation on the bandwidth with which we can modulate? Well, in principle, the modulation bandwidth, simply put, will then be limited with the clock rate with which you modulate. Just like in any other digital to analog converter, we have to respect the old-fashioned Nyquist rate. Note very importantly that an all-pass transfer to the output also means a no-pass to the loop. What that means is that the modulation data is completely cancelled in front of the phase error detection. So in other words, our loop filter, our loop in fact, is completely intact with the modulation data. It's completely oblivious to the modulation data, and it sees the same voltage variation it would have during normal fractional synthesis. So it's completely insensitive to the modulation data. This, of course, is true exclusively, all of this theory is true exclusively, is if injection is accurate, or in other words, if both point 1 and point 2 do not have any kind of gain or nonlinearities in the injection. Moreover, it's important to note that we also must ensure that the injection doesn't have any kind of time inaccuracies. We will look into that in a second. Just like in classical PLLs, we can also operate the DTC-based subsampling PLL as a phase modulator. The modifications you need to do in order to enable a modulation using the PLL are trivial. The phase modulation data can simply be injected in front of the DTC. Injecting only in a single point within the PLL will result with low-pass transfer of the data to the output. This effectively means that we will not be able to modulate beyond the bandwidth of the PLL. However, a subsampling PLL is a wideband PLL, so you might get a little bit further using this loop rather than a classical loop. Phase modulation can be also observed from the time domain. What's going to happen is that a DTC will, under the influence of the modulation data, simply enforce certain error, or it will on purpose subsample away from the zero crossing to make sure that the VCO accumulates desired modulation phase. Note that as long as the modulation data is low in frequencies, the variation around the zero crossing is going to be slow, and we will not have large instantaneous errors. Hence, the PLL will be capable of changing its operating frequency. The loop will have time in order to change, in order to react to the modulation data. So if we would try to modulate with high frequency, in time domain, what that means is that the DTC would try to induce larger errors or subsample further away from the zero crossing. That has several consequences. First one is, well, the PLL will not be able to react fast enough in order to really instantaneously shift the operating phase by this much. So this will take certain time, and that's where the low-pass filtering in fact comes from intuitively. Another important thing is that with subsampling away from the zero crossing, we will enter the region in which the linear range of phase error detection gain is not anymore respected, and this might impose additional distortion in the system. For example, if you want to push this process even further, we might try to pre-distort the data, as we originally explained. But what that means in the subsampling domain is the following. In time domain, pre-distortion means we will increase the instantaneous purposeful errors even further in order to compensate for the final reaction time of the PLL. And our concerns from the previous slide related to linearity are now even more pronounced. I mean, we could even induce clipping since we have a limited linear detection range. So this is not really a way to go if you want to extend the modulation bandwidth when it comes to DTC-based subsampling environment. To achieve a true all-pass of the data to the output, we can use, again, two-point modulation. In context of a DTC-based subsampling PLL, this means that we will inject the modulation data twice into the system, once in front of the VCO, and for the second time through the DTC. The point 2 follows a high-pass profile to the output, and the point 1 through the DTC follows a low-pass filter profile to the input. When added together, we truly get an all-pass of the data through the output using this hybrid loop, where we use digital modulation in point 2, digital modulation in point 1, but an analog subsampling loop. Note that this all-pass of the data to the output also means that we have a no-pass of the data to the input, or in other words, our filter will be completely resilient to any modulation data. It will operate independently of our modulation data without any awareness of it. What that means in the time domain is the following. So point 2 will simply enforce change of the operating frequency of the VCO in such a way that the original zero crossing during fractional-N synthesis will be moved. Since the DTC is aware we are trying to pass this signal to the output, the DTC will receive the information about the amount of phase error that we accumulated on purpose, and it will still enforce the zero cross subsampling. In this way, we are still sampling exactly near the zero crossing, and then there is no concern about going beyond the linear detection range of the phase error detector. Since the DTC now again subsamples the zero crossings, the PLL operates in the range where all small signal approximations are again correct. What that also consequentially means is that we will be capable of reusing all our calibration algorithms once again, because there is no virtual change with respect to how the basic loop had been operating in fractional-N mode. In this way, we already compensated for half of our problem. So any kind of 0.1 inaccuracies, DTC gain or INL errors can be recalibrated out as explained previously. At the same time, we could also have a lot of gain or nonlinearities in 0.2 injection. For example, we could have nonlinear capacitance to frequency conversion, especially at wide bandwidths. To compensate for the nonlinearities or gain imbalance in digital to frequency conversion related to 0.2 injection, we can reuse the same calibration principles that we used in order to calibrate our 0.1 injection, or in other words, the DTC gain or nonlinearities. The only difference over here is, of course, that the lookup tables are going to be populated based on correlation with the DTC input code. Thanks to the fact that the DTC input codes and the DAC input codes can be decoupled one from another, it is possible to operate all this calibration in the background simultaneously. And in this way, the DTC-based subsampling modulator can operate without any gain or nonlinearity imbalance during two-point modulation. Once again, background calibration simply means that two-point injection gain imbalance and nonlinearities are resolved. The DUC induces the desired frequency shift, and the DTC induces the desired time delay. Although there are no gain or nonlinearities in the two-point injection now, there could still be some timing inaccuracies. So for example, the DUC could induce correct frequency shift, but at a wrong moment in time. Where could that come from? You could have this effect coming from, for example, a non-instant frequency shift in the VCO, right? The VCO does not react immediately, or you could have certain amount of clock skew in the injection. This effect is not that relevant for slow modulation, but when you're looking into modulation bandwidths beyond 10 MHz, it might have an impact on your system. So we will look for a couple of slides. Let's assume that we desire to shift the operating frequency of the VCO at every falling edge of the clock. And let's also assume that the VCO has no gain or nonlinearity in injection point 2, or in other words, that it actually does the correct frequency shift. But it does the correct frequency shift at the wrong moment in time. In fact, the difference between the moment in time at which we expect the frequency to change and the actual moment at which the frequency changed, we will indicate that time with tau d and call delay spread. A consequence of delay spread will be that the VCO will start accumulating phase at a different frequency at the wrong moment in time. And the DTC, if not aware of delay spread, will simply subsample at the wrong place away from the zero crossing, and the PLL will try to compensate for this effect, creating distortion in the signal propagation path to the output. It is important to note that our two-point phase modulator can still propagate linear information to its output, given that the DTC is informed about the amount of delay spread in the system. In other words, we can still pre-distort the DTC input code so that it subsamples the zero crossing and so that no undesired loop filtering is imposed on our modulation signal. To do that, we use the correction coefficient C, which actually indicates the percentage of the time of the full reference cycle at which we operated at the wrong frequency. So in presence of no delay spread whatsoever, then C is simply 0. And the code sent to the DTC, or the phase modulation signal, is computed only based on the given modulation's cycle frequency change. If, however, there is a certain amount of delay spread in the system, then C simply becomes a non-zero value. It will be some small value in between 0 and 1. And then the DTC input is going to be computed for phase compensation. It will be computed not only on the given cycle or on the last modulation signal frequency change, but also on the one in the cycle before. And in this way, the DTC still subsamples the zero crossing, even though there is a delay spread. And you can, in principle, manually set the C coefficient for accurate two-tap based pre-distortion. Alternatively, the necessary correction coefficient C can be calculated in the background. And to enable background estimation of this correction coefficient, we need simply to track the correlation between the change in the modulation signal and the instantaneously measured error sign. And the correlation here is executed based on multiplication and then integration with certain scaling of these two signals. C will then simply drift towards some positive or value which will correctly estimate the amount of delay spread in the system and ensure that the DTC subsamples the zero crossings on average, independently of what frequency modulation signal we desire to have at the output. Finally, this means that we are operating in a two-point injection environment that operates effectively without any injection gain or nonlinearity imbalance, thanks to the background calibration algorithms. Moreover, we can operate without any timing mismatch. Hence, it's gonna be possible to modulate at any desired modulation bandwidth. In the core of a system, we still have our low noise synthesizer, the Subsampling PLL, which actually remains operating with performance equivalent to integer n operation, or the section 1 of our talk, thanks to the fact that there are no nonlinearities or timing mismatches, and that, as explained earlier, can lead to very efficient communication, very spectrally efficient communications, since the measured EVM will typically be very low. With my final slide, I would like to leave you with three key takeaway messages. The first one is we showed how an analog subsampling core can really enable extremely low noise operation and low power environments for high figures of merit. The analog subsampling core has a very high phase error detection gain, which leads to power efficient suppression of any in-band noise within the system. The second takeaway message is that DTC is a very powerful phase modulator. A DTC is a block that can operate with low quantization and low analog noise, hence you will be able to get the most out of your system. Finally, for fractional synthesis and for modulation to be truly accurate, in order to truly operate with fractional accuracies or modulation accuracies that are equivalent to the integer n basic subsampling operation, we can look into digital background calibration engines, and these can be implemented very efficiently in the modern nanometer CMOS, and can enhance and give you the best out of your analog subsampling core. Please note that in my references you will be able to find more information about the basic integer n subsampling PLL if you're interested, about digital to time conversion principles. You will also be able to find additional material on fractional-N subsampling synthesis, and also on randomization and background calibration techniques for DTC-based PLLs.
references related to phase frequency modulation, if you're interested, are listed on this slide.
Thank you kindly for your attention, and I am already looking forward to any questions you might have about my talk.
Hi, Nereo. Hey,
Hello.
thanks a lot
Yeah.
for this fantastic lecture. We have a bunch of questions, and so just to let folks know that you've already been answering some of the questions that people have asked. That's one of the benefits of doing the pre-recording, is that frees you up to answer questions real time.
Right.
There were a couple questions that came up, I can see. One is, so I'll just look at the questions that you have not had a chance to answer. And unfortunately, I'm subsampling on the questions that are showing up in WebEx. But one question is, the on-pulse of the transconductor of the sampler is a fraction of Tref. Is the PLL dead during the time the transconductor is not acting?
Right. So indeed, the PLL corrects for phase error once every reference cycle. In a subsampling PLL, indeed, charge is injected into the loop filter during this duration of the on pulse, and then it stays idle until the next comparison cycle. This is similarly true, for example, in a DTC-based PLL. The PLL also stays idle between the two cycles because you measure some error at one reference edge, you correct the error by changing the loop filter output in that cycle, and then everything stays fixed until the next reference edge when everything is clocked once again. So yeah, the PLL stays idle in these periods in between. And if you want to produce more correction and have your loop, let's say, correct more often in order to suppress more and more noise, then you need to have the reference on a higher frequency. The reference rate has to be higher than, or the PLL multiplication number smaller.
I mean, correct me if I'm wrong. I mean, my simple understanding of this is, you know, because you are doing a sample and hold at the front, you are literally holding that voltage over the duration of the ref clock period. And so that enables you to modulate the VCO to accumulate or retard phase very slow or more gradually, or as gradual as it gets over the entire duration of the ref clock period, as opposed to classical PLLs with a charge pump where you're just squirting a little bit of change at the beginning of each ref clock period for the correction to happen. That's why you need that typically the loop filter.
Yeah.
You have that RC for compensation plus another parallel shunt capacitor to kind of smoothen out that waveform, right?
Yeah.
And
we do also have that filter in subsampling.
Yeah, I realize that. So, my question is, if you're already smearing out, whatever area, so to speak, underneath the phase versus time, or voltage versus time, you're already smearing out across a ref clock period. Do you need that secondary capacitor there?
Do we need a secondary capacitor?
So you've got an RC for compensation,
right.
R for compensation, for lead compensation, right? And then you've got a parallel capacitor, shunt capacitor in that. And, the textbooks say it's typically about 1/10 of the value. It's meant to smear out the
yeah, but you do want that shunt, that this or parallel capacitor to absorb like the instantaneous injection during the transitions. Like that basically helps you to get this high frequency pole in the system that has benefits for capturing high frequency noise better.
Okay.
So that helps, yeah.
I see. So there's still value in that, right?
Yeah, there is value in that, indeed.
I see. Okay, that makes sense. Yeah. Another question that came up in the phase detector sampler, the noise contribution would be both from voltage amplitude noise and time jitter noise at the zero crossing, vis-a-vis classical PD working on time edges only.
Yeah, so you operate so close to the zero crossing that you can approximate phase errors, that you can approximate VCO waveform variation with only phase error. Strictly speaking, let's say, like if you're in the zero crossing and the amplitude changes substantially, that does instantaneously change the gain with which the phase error is detected. But that's in the range that it's so small that it doesn't impact the loop stability or the filtering properties of the subsampling PLL. So the simple answer to this is just you can approximate, thanks to the fact that you operate so close to the zero crossing, this loop operates in a small signal environment where you can approximate any form of variation in the VCO exclusively with its VCO with its phase noise error.
Got it. Now, I was going to ask, are there any special considerations in how you build that sample and hold? Obviously, you know, like
right.
I assume the standard tricks to make sure you don't have a charge injection, clock feed through, you know, disturbing that, because that immediately translates to giving the loop basically the wrong information to the VCO, right?
Yeah, indeed. And it's also the kickback from the sampler to the VCO. So that is the critical one. So all the tricks from the ADC world, where we take a lot of care about how we built our sampling switch, can be applied over here. All of this parasitic charge injection can be injected back to the VCO, which will instantaneously modulate the VCO operating frequency, and you want to avoid that. So what we typically also do is we place a buffer to isolate the VCO output from the sampler itself to ensure that there is less sensitivity to these kind of events.
Okay.
Yeah,
that makes perfect sense. Okay. And when this is in the feedback path that you're referring to.
Yeah, in the feedback path. Yeah, of course, that will result with added power consumption, which is almost which doesn't have any other use but to isolate the sampling event. So the parasitic injection. So yeah, that's a trade-off that needs to be there. Right? But indeed, all the tricks where you make sure that you compensate charge injection by having dummy switches, or that you have let's say differential clocking and so on and so forth, can be used in order to minimize these negative effects.
Got it. That's interesting. And I'm thinking out loud here, but I would imagine you talk about the kickback from the sampler back to the VCO through the feedback path. Ironically, I mean, could there be possibilities if you were to have some serious kickback that the switching of the sampler could actually be sending a signal that the VCO could injection lock to?
Yeah, well, actually, an extreme case of what can happen is that you have some form of, imagine you have a sample and hold, and as you take you could have some form of BPSK modulation at the output, because for a period of time you keep the switch closed and then you open it, so you modulate the instantaneous load on the VCO. So in an extreme case, you can have this situation where the VCO frequency jumps up and down at the reference rate, and that creates this reference spur, which is undesirable. So in a way, you are right. Yeah, you can create some form of this results with unwanted behavior of the VCO, typically very nicely measured in context of the reference spur you have at the output. So indeed, again, this is definitely something that you want to avoid.
Got it. Now, are you seeing any questions show up in the window? Like I say, I apologize. WebEx has done a number on me again.
Right, okay, I see here a question, for example. I'm just going to go from bottom up because there is a lot of questions popping up. So is the DTC inherently monotonous? Yeah, I think that's the healthiest thing the healthiest thing you can do during the design. You just make sure that when you design your data converter, there is no that it remains monotonic simply by doing your math correctly, doing sizing that it passes, statistical variation you might encounter in the technology that is being used, because non-monotonicity in the DTC can cause issues not only in context of instantaneous spurs you create, but also with calibration. So we typically make sure that just by design we guarantee the monotonicity. So that's how the approach that we take. Okay, so yeah, I see some other questions popping up here. Okay, so what about the gain of the PFD in the auxiliary path? Is that related to the smoothing factor, smoothing capacitor in the loop filter? Yeah, so the smoothing capacitor in the loop filter is part. So the auxiliary loop, you can compute the gain of the auxiliary loop, and that this loop also has to be stable, and you compute that that gain just like in any classical PLL. You can make an auxiliary loop which is actually a classical fractional-N PLL, and you just need to make sure that that loop is stable, and thanks to the fact that that loop operates with a dead zone, the transition from one loop to the other is smooth. You can reach, for example, with a 40 megahertz clock, 10 gigahertz output. So that's a multiplication factor of about 250. Locking time is typically in 10 microseconds or something, or less. But it's if you start from incorrect frequency. Would you get some benefits of subsampling with a DCO? With a digitally controlled oscillator, so all digital solution rather than VCO. Well, the subsampling PLL is an analog loop, right? So if you have a DCO, then you have added noise of the digital to analog conversion in front of the voltage controlled, or in front of the controlled oscillator. In a subsampling PLL, you have analog information passed to the VCO, so there is no added noise in digital modulation of the controlled oscillator. So it's if you prefer to have, you can indeed have a subsampling digital subsampling PLLs. You can simply put, for example, an ADC at the output of your sampler, and then you have your information in the digital domain. And you can post-process this information also in the digital domain with a digital loop filter. Of course, you can take that approach if you want to avoid using any kind of analog filter and you want to reduce the area of your chip. But digitization of the loop adds additional quantization noise, which is not there if you use an analog loop. So that's the trade-off you have to think about. I have to go.
I've got several other questions I'd like to ask along the way.
Go ahead.
So related to you made mention in answering this recent question about 10 microsecond lock time or so. So this is a segue to my question. Have you been exploring tricks and opportunities of what you can do with a subsampling PLL scheme to speed up lock time?
Yeah, so say that you need to only phase lock, right? So that the correct frequency already exists at the VCO output, and you only need to make sure that the PLL locks the residual phase error that we had at the output. Then the simplest thing is, of course, to just have a wide loop bandwidth, because that ensures that the error is compensated very fast. That's in context of only having a phase error, meaning only in a situation where that's in a situation where the subsampling is good enough, right? So there is no need for the frequency acquisition loop, because the error at the output is not larger than one integer n, right? So it's within the frequency error is not larger than one fref. if the frequency error is larger than 1 FRF, then you need help of the auxiliary loop. So in order to make things fast, in order to lock the PLL as fast as possible, then the same trick applies. You want to have a wide bandwidth in the auxiliary loop. I did investigate, and there are papers that deal with also speeding up the transition from one loop to another. What you can do in order to speed up the locking is, in these extreme cases where the error at the output is larger, so large that you need both loops to simultaneously operate, or auxiliary loop to operate first and then the subsampling loop to take the error back. To continue the phase lock. So you want the dead zone can be reduced. So the smaller the dead zone, the faster the locking process is. Because you need less phase error to be accumulated in order for the auxiliary loop to activate. So things get faster. So like if you really want to optimize the locking process, you can play with the dead zone and with the bandwidths of the subsampling loop and the bandwidth of the auxiliary loop. And to speed things up, the dead zone should be small. In the extreme case, you can even have a dead zone that is only half of the VCO period, for example. So on all the range outside, the auxiliary loop will be active, and it can have wide bandwidth so that it corrects for things fast. And once when you detect a phase in between, then the subsampling takes over. So that's kind of my thinking when it comes to speeding up the lock process.
Got it. Makes a lot of sense. Another question. I mean, in terms of applicability of using subsampling PLLs, where do you see people actually building subsampling PLLs, and you know, is this something that you're already seeing in products?
Yes, I think they are used in products. I've seen that for low jitter environments, especially when like I personally have experienced seeing these in context of producing low jitter clocks for ADCs, maybe where fractional accuracy is less relevant. Then subsampling really ensures for low power a very high accuracy clock, which is in ADC extremely relevant, especially in these days where with these new standards you get a specification such as 10 femtoseconds of jitter or something. So that's where subsampling plays a big role, I think. Yeah. So yeah, I've seen it. I've seen traction in picking it up for these, also in context of these communication, high-speed communication standards. At high frequencies, so beyond, like for example, in 60 gigahertz range, I'm not completely sure, but at lower frequencies, sub 6 gigahertz range, I've seen it as well. Yeah.
Awesome. Anyways, I'm done with my questions. Nereo, if you don't see any questions left, you know, I want to just have this opportunity to thank you once again for this wonderful, excellent lecture. I mean, I saw some comments feeding in. People are very appreciative of you taking the time out of your busy schedule to help edify us on this growing topic of importance and interest in our community.
Thank you so much. It was really a pleasure to join in. Hopefully next time it will also be in person because San Diego is always a beautiful place to be. And
you're always welcome here. It happens to be raining right now, which is very rare, but but certainly you know, you have an open invitation to come here anytime you like. Yeah. And
thank you
in person.
Thank you so much. Thank you.
Okay. Yeah. Thanks again, Nereo. Yeah. Take care. Have a good weekend.
Likewise. Bye-bye.